right? Right. So we need to talk about balancing as we go. So zinc solid plus copper 2 sulfate solution yields zinc sulfate and copper solid. Here's how we balance, and I know that some of you guys have a good background on this and others don't, so I'm just going to walk through kind of slow the first two. So how many zinc atoms do I have on this side? 1. How many zinc atoms do I have on this side? 1. How do you know it's 1? Say again? What's the subscript behind this ZN? There is a 1 here because I reduced my sulfurs and zinc 2s down to 1s. Okay, so that's 1 zinc and 1 zinc atom. How many copper atoms do I have? 1 copper atom here, and on this side, 1. So these coefficients of 1, 1, 1, 1 so far are, the coefficients are distributed all the way across, whereas the subscript is only correlating with that 1 atom it's attached to. Okay, now I like to keep, so since you guys can see sulfate and sulfate's the same on both sides, right? So I like to think of sulfate as one happy family. How many sulfates do I have on this side? 1. That 4 is a part of sulfate. That's not describing 4 sulfates, right? If there were 4 sulfates, I would have a 4 back here, right? That's not the case. I have 1 sulfate. So I have 1 sulfate here. How many sulfates? Here. 1 sulfate. So I have 1 of everything in this case. It's balanced. There's no inequalities on each side. If you don't like to keep sulfate as a happy family together, you can break it down into 1 sulfur, and then 4 oxygens, but it would still yield the same thing. All coefficients must be 1. Okay, so here's the rule of thumb. Once you've written out your equation in terms of like all the names went to formulas, do not touch your formulas. Your formulas are right. Don't change any subscripts. The only thing I'm adding at this point is I'm adding coefficients. Where do the coefficients go when I'm balancing? In front of the number, okay? So don't mess up your awesome like nomenclature. It's already done. Don't change that. All right, so magnesium chlorate is heated. Magnesium chlorate, give me a thumbs up, MgClO3, 2. Thumbs up, you got that? Okay, if you didn't, you're a little behind here, but we're, like I said, nomenclature is now standard, you should know. We're going to be applying it to reactions from here on out. Okay, so magnesium chlorate solid yields magnesium chloride, which is a solid as well, S, and gaseous oxygen. Now, who did not put a 2 on it? And that's okay. We're going to work on getting to know that when I say gaseous oxygen, we're talking about the big 7 in hydrogen. Diatomics, do you guys remember the diatomics? We wrote down this little cheat sheet. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Remember that? Those are the diatomics. And if they're by themselves, like it just says oxygen, it doesn't mean just oxygen. It has a little mini me with it, meaning O2. It's diatomic as in nature itself. And then hydrogen is the last one. So it's big 7 in hydrogen. Yeah? Okay. So this is O2 gas. So as we go here, we need to look at balancing. How many magnesiums do I have in the reactants? 1. There's a 1 right there behind the magnesium. How many magnesiums do I have here? 1. Okay, so I always like to start with 1 element and move forward, look at each one of them individually. So magnesium's balanced. How many chlorines do I have on this side? So do we see this distributive property of this subscript? This means that goes into the chlorine and it multiplies by the oxygen. So that is 2 chlorines on this side. How many chlorines on this side? 2, because of the 2 right here behind the chlorine. All right, so chlorine and magnesium are balanced. Okay, how about oxygen on this side? How many oxygens do I have? 6. 2 times 3 is 6 on this side. 2. So that's not balanced. So what do I add to make it balanced? 3 where? I only add coefficients at this point, right? Coefficients are the only thing I'm using to make sure I'm balanced. So I have a 3 in front of my oxygen. Now I'm balanced. Who's picking up what I'm putting down? Awesome. Okay. It's been a little while for some others because you do a little bit of this in middle school. Okay. So next is we have solid sulfur, S, with oxygen gas, diatomic. You guys balance that. Work with somebody at the table. Okay, so how many sulfurs do I have? 1 and 1. Okay, how many oxygens do I have over here? 2, and I have on the side 3. Okay, so I can't really get 2 to 3 without multiplying. But if I want to multiply 1, I actually, because there's not a, what do you call that? What's the least common multiple? Is that the right mathematical term? Okay. What's the least common multiple between between a 3 and a 2? 6. So I'm basically gonna have to get them both to 6. So if I saw this 2 here and I was like, I saw this 3 here, I was probably gonna go, oh, I can multiply this one and this one by 2 and 3 opposites to get 6. So if I put a 2 coefficient in front of this one, I have how many oxygens now? 2 times 3, because that coefficient will distribute all the way across. 2 times 3 is 6 oxygens. And on this side I only have 2, so what coefficient do I need? A 3. Okay, so that 3 times 2, again, is 6 oxygens. Now, I already looked for sulfur, and I was like, yeah, sulfur's good, but now what do I have with sulfur? I have a 2 with sulfur, so now what do I need to add over here? A 2 coefficient as well. So just kind of do that last reflective look to make sure everything's still balanced with you adding coefficients involved in everything. So far, so good? Okay. And then got a couple more. All right, so we have silver nitrate and sodium bromide yielding sodium nitrate and silver bromide. So you guys tell me, what are we going to start with? What element are you going to start with? Let's just go in order, right? So Chloe, how many silvers do I have? 1. 1 on this side and on that side? 1. Okay, Lindsay, let's do individual elements. So what element do you want to do next? Nitrogen. Okay, so nitrogen, how many do I have? 1. 1, and on that side? 1. Okay, Robbie, how many oxygens? 3 and 3. Okay, wonderful. Nick, sodium? 1 and 1. Suraj? Bromine 1, silver 1. Okay, 1, 1, 1, 1 all the way across. So what's my ratio with my coefficients? 1 to 1 to 1 to 1. Right, okay. Wonderful. Nice. Let's keep going. You should be checking your nomenclature as we go. Yeah.
Do you want us to put the ones?
You don't have to. No, I'm just making sure that you actually know there is a 1 there. Yes.
So with number 3, did we have to put a 1 in front of the oxygen? Or
And this one right here?
oh, we started to add.
We had a 3 there actually because we balanced it by making 6 as our net. These? Okay. All right, so next one we have liquid water, H2O, and then, oh, I didn't look back to see if I put the catalyst on here. Put it back there. Got your ninja skills on today. Okay, so water is going to be electrocuted basically. So if there's a condition involved, you write it above the arrow. So I'm just going to put electricity like that to say it's electrolyzed. Is applied to liquid water decomposed with hydrogen gas and oxygen gas. Again, these are diatomic. That's probably one of the hardest things to remember is when are you writing diatomics. But your big 7 in hydrogen will be your reminder. Okay, so how many hydrogens do I have on both sides? 2. How many oxygens do I have on both sides? 1 and 2. Okay, so I need to get the 1 up to 2, so I'm going to add what? A coefficient to water. Okay, so that 2 applies to oxygen. Great. So that means that there's 2 oxygens, but it also applies to hydrogen. So now that I have 4 hydrogens on the reactant side, I also need 4 hydrogens on the product side, so I'm added 2 there as well. So it's just a baby step process, right? Okay, keep going here. Mercury 2 oxide is heated to produce mercury solid and gaseous oxygen. Again, this mercury 2 oxide, mercury 2 and oxygen, 2s and 2s reduced down to 1 and 1. So this might be one you had a hard time with. But then mercury liquid and oxygen gas, in this case oxygen's diatomic. What's my only thing that's not balanced? What's my only thing that's not balanced? Say again? Okay, so what would I add according to this equation? 2. So a 2 in front of the reactant, mercury 2 oxide. And then that 2 applies to oxygen and mercury. So then I need 2 in front of mercury. What's up?
It says in the problem that a product with solid mercury, not liquid.
Oh, yeah. This is a mistake. What's our general rule for mercury at room temperature? It is liquid. So my brain overrided my phrasing up here, so it's truly liquid. If you put solid, no biggie, because it's just a state of matter. Okay, and got a couple more. Aqueous solution of potassium iodide and aqueous lead-2 nitrate react to produce solid lead-2 iodide in solution of potassium nitrate. So we have Ki PbNO3 2 yields PbI 2, and or KNO3. Sorry. So usually when you start to see these, your brain should start kicking into the names versus spelling, because I could go, hey, EMILY, right? No, it just sounds stupid. So I don't always spell the names out, so I usually just say the name like this. Okay, so what are you guys seeing that's first thing that's not balanced? Iodine. All right, so you have 2 eyes here. You have 1 eye here, so what do we want to do? Add 2 where? Potassium iodide, okay. Now, I've just caused 2 iodines and 2 potassiums. So I got 2 potassiums on the on the reactant side. Now, add 2 where, Miles? You got this, man. Name. Potassium nitrate, right. So put a 2 in front of potassium nitrate. Well, again, do you see that nitrate never changed? It's still nitrate from reactants to products. So I'm actually going to try this another way with you and say, let's put a parentheses around your nitrate. So that 2 not only says, do I have 2 potassiums, but I also have two total nitrates. How many total nitrates do I have on this side? 2. So I'm good there, right? Leads? Good or good? 1 lead here and 1 lead there. Good. So I'm making sure that this 2 is not correlating with anything but nitrate. That 2 does not correlate with lead. Okay. Are you guys doing okay so far? Yeah? And I think I got 2 more here. 3 more maybe. Solid aluminum reacts with oxygen gas from aluminum oxide. What is aluminum oxide's formula? Al2O3. That is, I swear, one of the hardest ones. People would just put Al together and they're done. Okay, so make sure you're crisscrossing there. So what's the first thing you see that's not balanced? Aluminum, okay. So if you saw aluminum here with a 2, you see it's with the 1 here, what do you want to do? Okay, so put a coefficient of 2. That's what most of us are going to do first. And then we see oxygen with the 3 and 2. Noticing you can't really just multiply one of them to get the number up. You have to do the least common multiple thing again, right? So what do you want to multiply these both by? 2 and 3, right? Opposite of each other. So this 3 one will be multiplied by 2. So that gives me 2 oxygens. And 2 times 3 oxygens, so 6 oxygens. And you put a 3 here to give you 3 times 2, 6 oxygens. But as soon as you did that, you then messed up aluminum, right? So now how many aluminums do I have? 4. 4. All right, let's change your 3 to a 4. That's a 4. So don't be scared to change your coefficients after you're balancing. Ooh, this one looks pretty interesting. MgCl2, thumbs up. We got magnesium chloride. Ammonium nitrate, NH4, NO3, thumbs up. Magnesium nitrate is Mg, parentheses, NO3, 2, thumbs up. And NH4Cl is ammonium chloride. So that nomenclature is really kicking us in the butt at this point. Okay, so what's the first thing you guys see is not balanced? So some of us are in chlorine, right? So if you want to go in order, like I was, like magnesium first, they're both 1s. So if you want that step-by-step process, that's your best friend. If you're just like, hey, I can look at it and figure it out, go with the flow. So there's 1 magnesium, it's good. 2 chlorines and 1 chlorine. So what do? Multiply ammonium chloride by 2. That's a 2 coefficient. So that 2 applies to Cl and everything else, right? So do you guys like to look at, because I can see that ammonium and ammonium is there together, do you guys like to look at the whole entire polyatomic ion or individual elements within it? The whole thing? If you see it, okay, I just, pick your poison. But that definitely is ammonium, and this is right here is definitely ammonium. Okay, so that 2 applies to chlorine and to ammonium. So how many ammoniums do I have on the products? 2. How many ammoniums do I have on the reactants? 1. There's a 1 after that parentheses, right? So that would be, I need to add a 2 to that to make it 2 ammoniums. Okay, that 2 also applies to what? Ooh, NO3, I heard people say nitrate. So that's a big happy family nitrate. Do you see nitrate on this side as well? Okay, this nitrate here already has a 2, so is that balanced? Yeah, because that 2 applies to a nitrate, and the nitrate here as well already has a 2. And we're done. We hit all the ions. We're good. Okay, I think I got one more with a catalyst. Yeah, this one, okay. So this is the one where most of you maybe forgot to put the catalyst above the arrow. So in the presence of manganese 4 oxide, which we call MnO2, that was on your little table above your reactions. So in the presence of this, it's basically saying this is a condition of the experiment. So this is actually a catalyst. It's something that's going to force the reaction to occur. So above your arrow, you should put MnO2, not as a reactant, not as a product. It's just a simple condition of the experiment. Just like you would have drawn heat, that triangle. I didn't draw the first one, but I'll go back and show you. So now you see phosphorus as one reactant, oxygen as another reactant, phosphorus pentoxide as a product form. So MnO2 is just a condition. All right, so what's the first thing you see not balanced? Oxygen. Okay, I just need some more space. So I'll write this real fast. So you see oxygen's not balanced, so what do you guys want to do? So these come in multiple things, so 5 and 2. So this oxygen gets a 5. So that's 5 times 2 is 10. And this whole thing over here gets a 2. So that 2 times 5 is 10. But now that means I have 2 phosphori, right? So I need a 2 over here as well. Okay, any questions on balancing? Yeah.
So how do you know if it's like a solid or gas?
If it doesn't tell you. So many times you'll know it's solid because it's a pure metal. So all of our pure metals over on the periodic table, if they're in their singular form, they're solids. All of our diatomics, these right here, these are all diatomic gases. So a lot of the nonmetals in their compound form will be gases. So that's reviewing back to, like, generally, if we're at a room temperature, all ionic compounds are solids, and all covalent compounds are gases. There's a couple in there that, like, it says solution of. There's no question it's aqueous. But that's usually the general rule of thumb. Good question. Yeah.
Is this going to be really easy in the future, or is it going to get harder?
So right here, this is all the stuff that's just balancing, looking at your equations, writing the formulas, balancing. That should be very easy. But what we're going to start to do is, you've seen I've given you reactants and products. What we're doing next is I'm going to give you reactants. You're going to learn to see the chemical reaction that's taking place, and you're going to predict your own products. I'm not going to give them to you. So it's going to get more application based than me telling you and you're like, okay, I can write it down based. Yeah.
Do you have to write the form, like the S and the G small? Or?
Yeah, generally it's small. Generally it's like a little subscript. Okay, so I will go ahead and tell you the 5 types of reactions, and I'll leave you alone for now. Okay, 5 types of reactions. Write these down someplace, and you'll see them. RxN means reaction for me. Okay, you'll see them in your reading guide. So if you're writing down homework as you go, reading guide 11 is so chapter 11 and 12 those are our next 2 ideas. Those are our next 2 chapters. And guys, we are actually at the peak of difficulty in chemistry. My personal opinion, but we're at the peak. So the next 2 weeks will be peak of reactions, stoichiometry, and pulling those together. And then we're going to kind of go on this nice downhill with gases and thermochemistry and states of matter. It's nice downhill after that. So that's my personal opinion, you know? So we'll kind of see how you feel about that too. But who's ever heard of a synthesis reaction? Synthesis. So synthesis is our first type of reaction. It basically takes 2 things into 1. Takes 2 things into 1. Huh. Look at that reaction right above us. Doesn't that take 2 things into 1? Mm-hmm. That's a synthesis reaction. Next type of reaction is a decomposition. Decomposition reaction. What does it sound like is happening? Things are breaking down. Thing or things are breaking down? Thing. One thing is breaking down. And I'll just say for now into 2 pieces, into 2 parts. It could be 3. It really depends on what the composition is. But in your, looking at your reactions you just wrote, tell me which one of those is a decomposition reaction. H2O electrolyzed into H2 gas and oxygen gas. That's 1 water breaking into 2. All right. Next one is a single replacement reaction. That's where one thing in a compound trades places with something else, single replacement. So let's kind of look back. One thing changes spots. Nothing so far. Okay. The very, very first one. So zinc and copper. Basically, what did they do? They just was like they were like done, switched, and that's all. The sulfate stayed where it was, and zinc and copper switched. So that's a single replacement reaction. So you're starting to recognize them as a single replacement. Okay. The next one is a double replacement reaction. Double replacement reaction. Can you guess what happens there? Two things switch, or it looks as if two things switch according to our reaction. Look for something in your Chem and tell me which one you think could possibly be as complicated as double replacement. Yeah, Rishi. Is that what is that one?
It's when silver nitrate.
Yeah, that one, right? Okay, so in this one, silver, it actually, because there's four compounds here, or there's four ions, silver, nitrate, sodium bromide, two things switch places. So like basically silver and sodium trade, but bromine and nitrate also trade. So that's kind of why it's called double replacement versus the single replacement. But we're going to get into these in much more detail. And the last one I don't think I have represented on your first set here. Oops, sorry, dang it. It's combustion. What does combustion sound like? Say again? I heard fire. Okay, combustion does not only mean fire, you pyros. You guys have combustion happening in your body right now. Pew, pew. Little mini explosions. Yeah. It's actually a combination of energy being produced and released, probably. Consumed and released. So cellular respiration in your body, sugar you ate for breakfast is reacting with what to make ATP? Sugar with oxygen. Okay, so combustion really just means reaction with oxygen. It does not mean fire. But there is some sort of energy component that's exchanged. And I don't know that I had one with that on there. So, all right, so that's it for me for right now. I need this half over here to go grab laptops. I'll get you guys in a second. I'm going to pull up instructions for the polymer card experiment or project. I also have to take attendance. Oops. All right, the rest of you guys go get your laptops. Wake Forest, huh? Is that where you're going? For golf? For golf? Oh.
I was the restroom once you like go over.
You okay? Just tired. Alright guys, as you're kind of pulling your laptops, I'm going to tell you where your information can be found. And then I'm going to leave you alone because I think this is pretty self-explanatory. So when you're getting on the onlines, you're going to go to my website. Last night you were supposed to just kind of look over the instructions, kind of see what we're getting into. But polymers and car summit, specifically root over summit, if you would like, you could have started researching. I already have some people who have claimed a spot here. But underneath the PowerPoint, you'll see this PowerPoint like this. It'll walk you through kind of like a thought process of brainstorming with a partner on polymers found in cars. And then you'll start to dig into a specific polymer, plastic or something like that found in a car. And as you're starting to dig, though, you can't dig until you have signed up on the Polymers in Cars class results page. So I already have a couple people who've signed up. You're supposed to sign up with a partner, okay? So you can see these people here have done their due diligence and they went ahead and signed up. They looked at the, I'll pull back up the top of the table. The item, where it's found in the car, the purpose, and then as you're researching, you're going to fill in some of this. It won't be like right off the bat, you're like, oh, I know everything here. going to take a little bit of just digging. But as you can see, these people have found theirs and they've claimed it. So you cannot claim something that someone else has claimed, but there are tons of options, guys. Don't get bogged down with that. But as you move on through it, it walks you through the next steps of the process, which would be you're doing a little bit more research about intermolecular forces, what the compound molecule looks like, as well as like why do we need it? Why is the property that it has, why is that so important in the car? And so you're just really taking chemistry and you're applying it to a real life scenario. And at the very end, the very, very, very end, I'll go ahead and scroll there. Not that one. The last part, which is what you'll be submitting to me next week, is a one-page summary of your findings. And so as you're finding things, save your sources. Don't just get rid of them, okay? Save your sources. And this will just be one page. And then as you have summarized, you should be educated enough to share a little bit about that next week. And that presentation part can just be an oral, like, share-a-thon with, if I'm sharing with Jillian about plastic, she's sharing about me. I can hold my paper in front of me and do a little oral share with her. We're just practicing some chemical language with each other. And if you don't want to do an oral, you can do like a poster or a quick PowerPoint. Please do not spend too much time making a PowerPoint. You've already done this, right? You don't want to double up and do a PowerPoint too. So really, you should be able to orally share. If you want like a visual for it, that might be helpful, specifically your molecule. Does that help? Yeah. If you want to, it's just putting more work on you, but if that's something you want to do, absolutely. Okay, so are you guys good to go? Get started. You have 25 minutes right now to work with a partner. Yeah, go to the lab station.